Hello students. Today in this session we will discuss about application of Ampere circuital law. In first application we have expression for magnetic field due to very long straight current carrying conductor, that is long wire you may say, at some point outside the wire and inside using Ampere circuital law. So before we go further, let us have a quick revision of what is Ampere circuital law. So we know that Ampere circuital law can be applied in this situation where you have many conductors. Say in this situation you have five wires or five conductors carrying current in different direction, and at point P, if we want to find out at point P, if we want to find out magnetic induction or magnetic field due to these five currents, how do we find out? So the law, Ampere circuital law says that you should take, sorry, you should take closed integration of magnetic induction over the Amperian loop, or line integration of magnetic induction over closed loop, is product of permeability and sigma I. What is B? Magnetic induction, line integral or line element, and integration is taken on this loop. What is name of this loop? Amperian loop. And then we say that it is product of these two, permeability of vacuum and algebraic sum of the currents enclosed by Amperian loop. And how do we determine which currents are positive, which are negative? So for that we use right hand screw rule. What is right hand screw rule? So place right hand screw perpendicular to the Amperian loop. So if this is the loop, then you should take right hand screw and place it like this. If this is the loop, place right hand screw like this. Okay. So first step is to place right hand screw perpendicular to the Amperian loop and then rotate it. How to rotate? So rotate it in the direction of line elements taken for integration. So these are the line elements DL, DL, DL. So how you are taking line elements? We are choosing in this manner. Rotate screw in the same fashion. Here, I would say that the rotation is like this. So, in whichever direction you see the screw advancing should be considered positive for the currents. So, in this case, if we rotate the screw, we will see that the screw will be advancing in upward direction, which indicates that I1 and I2 should be considered positive, whereas I3, I4, I5 should be considered negative. So that is how we can use it, and this is the expression. Left side is line integral of magnetic induction over closed loop. Right side is product of permeability of vacuum and sigma I. Okay, so this is the law, and with this law clear, we can go to the first application, which says derive expression for magnetic field due to very long straight current carrying conductor. And we are supposed to find out expression at some point outside as well as inside. So let us first consider a current carrying conductor. So let me consider this wire which is having, say, radius r. Okay, and let there be some point. Let me consider this as axis of the wire. Okay, and let there be some point P, say here, and where is point P? Let it be at distance y. So this is the situation, and let the current be I. So for this situation, we want to find out magnetic induction at point P due to this straight wire carrying current. So how do we get it? Let us apply Ampere Circuital law. So what the law says? The law says that we should take line integral of magnetic induction over closed loop, and it should be equal to mu 0 sigma I. So first of all, I'll have to consider Amperian loop. So I should have Amperian loop passing through point of interest. So this may be the loop, or else let us consider perfect circular loop. So say this is the loop, okay, with radius y. And now, secondly, I'll have to choose in which direction I will take line elements for integration. Should it be like this? Means first your dl is here, next dl is here, next dl is here. So in that case, the integration will be going like this. So if we choose dl, that is line element for integration in this fashion, then what is the direction of current, positive or negative? So again place right hand screw, okay, and rotate it in the same fashion, and then you will see that the screw will advance in upward direction, and our current is also in upward direction. So this I should be positive or negative? It should be considered positive. Okay, so right hand side is mu 0 into I, because you have single conductor. Okay, we don't have I1, I2, I3, so right hand side is simply mu 0 into I. In the left hand side, can we write this as B closed integration dl? It is allowed or not? Now, before we go further, let us make this point very clear. See, when you have A dot B, can we write this as AB cos theta? Okay. Now, suppose somewhere if you see that vector A dot vector B is simply AB, what should be your conclusion? Your conclusion should be cos theta must be 1. So let us verify that what is DL, what is B, and what is the angle between the two. So let us check it first. So when you have current going upward, and if you consider some point P here, if you apply right hand thumb rule, so if you place thumb in the direction of the current, and then if you look at the curling of your fingers, you will see, you will realize that the curling is like this, isn't it? So magnetic field lines around this wire are going like this. So at P point, what is the direction of magnetic field? It will be going inside. Okay, so we can say that vector B can be written as minus BK cap. And when I imagine Amperian loop, okay, say Amperian loop is like this. So this is my DL, this is my DL. So when I come here, DL will also have the same direction, isn't it? So when I take B dot DL, actually I am talking about BDL cos 0, because angle between B and DL will be 0. So, and what is cos 0? Cos 0 is 1. So you can always write B dot DL as BDL. Okay, and this is true wherever you consider point P, not necessary that here only. If you consider point P here, or if you consider point P here, at all the points on Amperian loop, you will find the same situation. Okay, so angle between B and DL will always be 0, and hence vector B dot vector DL is BDL. You can write it as BDL. And as magnetic field at point P is constant, whatever is the value, B has to be constant, and then we can write the B outside the integration. Cos theta is 1, and then we are not wrong if we write vector dot vector B dot vector DL as BDL. Okay, because cos theta is 1. So that is one thing. Now what is the integration part? So can I write this as 2 pi y is equal to mu 0 I. Because see, closed integration dl means what? You are summing up, dl, dl over the circle, so ultimately you will get circumference, isn't it? And hence, closed integration b dl can be written as 2 pi y, and then make b subject of formula. So b is equal to mu 0 I by 2 pi y. This is the expression for magnetic induction at given point due to straight current carrying conductor. And if you remember, we had very similar equation using Biot-Savart's law also. There also we had a similar equation when we considered special case for infinite wire. So this is the expression. Now, what if we are asked to determine magnetic field at some point inside? Say my point P is somewhere here. How do we determine magnetic field then? Okay, let us check that also. Before that, have a look at the answer. Consider a conductor of infinite length carrying current I as shown in figure, and let there be point P outside the conductor. And where is point P? Point P is considered at distance y. And what is the first condition? First condition to use Ampere's circuital law is to have Amperian loop passing through the point. So this green one is Amperian loop passing through point P and closing the wire. Second step when you are applying Ampere's circuital law is to determine this. What is this? How you are going to integrate. So according to this figure, integration is going to take place like this. And hence, if you apply right hand screw rule and you rotate right hand screw in this fashion, you realize that it will advance in upward direction. So currents in upward direction should be considered positive. So I is positive or negative? It should be considered positive. And with that, we applied Ampere's circuital law, and this is where we are. Now in left side, as I mentioned, that angle between B and DL is 0, cos 0 is 1, so B dot DL can be written as simply B DL, B being constant can be taken out, and closed integration DL will give you circumference of Amperian loop. And ultimately on simplification, this is what we get. Now what if the point is inside? So if the point is inside, so let us consider that the conductor is having radius r. Let us consider that the conductor is having radius r, and let there be some point P. Where is point P? Let it be here. Here means again we consider it to be at y distance. Now in this case, we know that the current passing through the wire is I, but what we are concerned with is the current through the Amperian loop. We are not concerned with the total current. How much current is passing through this part? We are concerned only with that. Okay. So how do we determine how much current is passing through this wire? So we say that say from pi r square, that is the total cross section of the wire, is carrying current I. And then if I consider only pi y square, I am talking about only this much part. So how much current is passing through this part? So current passing through this part can be given as pi y square upon pi r square into I. Or else we can say that sigma I in Ampere's circuital law is now y square by r square into I. So we'll use this in Ampere's circuital law, which says that closed integration B dot dl is mu 0 sigma I, and as I mentioned earlier, left side can be written as closed integration B dl, right side is now mu 0 y square by r square into I. Okay, so left side is again circumference, that is 2 pi y, and right side is mu 0 y square by r square into I. Simplify this, what you will have, B is equal to mu 0 I y upon 2 pi r square. This is the expression for magnetic field at some point inside at y distance from the axis where y is less than r. Okay, so now we have two expressions for magnetic field due to straight wire. This is the first one, mu 0 I by 2 pi y. What is y? What is y? Distance of the point where we want to find out magnetic field, and y is greater than the radius of the wire. Okay, and the second equation is this is the second equation. So let me note down both. Outside the wire, B is equal to mu 0 I by 2 pi y. Inside the wire or inside the conductor, B is equal to mu 0 I y by 2 pi r square, where r is the radius. So I can say that when you are outside, B is proportional to 1 by y, and when you are inside, B is proportional to y. Okay, that is the distance from axis. So if I plot the graph, if I have to plot the graph of B versus y, what should be the nature of the graph? So this is the relation inside. So from center, as I go up to radius, this is the y is equal to r, and up to that B is proportional to y, so straight line. And what is happening outside? Outside it is decreasing, so magnetic field would be going like this. So that is the nature of variation of magnetic field with distance. This is the magnetic field outside, here is the magnetic field inside. So when you are inside, magnetic field is directly proportional to the distance. If you are outside, it is inversely proportional to the distance, and this is noteworthy point. B is maximum at the surface. Magnetic field is maximum at the surface, and this is the nature. So that is about first application of Ampere's circuital law, magnetic induction or magnetic field of straight wire at some point inside and outside. I hope you could understand. It is all for now. Thank you.